All right, let's talk about what is, without a doubt, one of the most important inventions in human history. I mean, it is microscopic, it's literally everywhere, and without it, our modern world, well, it just wouldn't exist. We're talking about the transistor.
So, to get us started, let me just ask you a question. What's the real engine of the modern world? I mean, really think about it. What's the one piece of tech that underpins almost everything we do every single day?
The answer is this tiny, unassuming, three-legged component. This right here is the transistor, and it is the fundamental building block of, well, all modern electronics.
So here's the game plan for the next few minutes. We're going to start with what this thing actually is, a tiny but mighty switch. Then we'll peek inside it, see how to flip that switch on and off, uncover the semiconductor secret that makes it all possible, and finally, we'll see how billions of them come together to create the digital brains inside all our devices. Let's get into it.
Okay, section 1, the tiny, mighty switch. So at its very core, a transistor is a device that really has two main jobs. It can act like a switch, turning a current on or off, or it can act as an amplifier, taking a small signal and making it much, much stronger.
Now, to really wrap your head around this, the best way is a simple analogy. Imagine a giant water pipe with a powerful flow of water rushing through it. That's kind of like your main electrical circuit, where current wants to flow from the collector to the emitter. Now, see that small little valve handle on the side? That's our control pin, the base. And here's the magic. With just a tiny, effortless turn of that little handle, a very small electrical signal, you can control that massive, powerful flow of water. A tiny signal at the base controls a much, much larger current. That's the whole trick.
And you have to understand why this was such a revolution. Before transistors, we had vacuum tubes. And as you can see, they were these big, bulky glass things, while transistors are microscopic. They were slow, kind of clunky, but transistors can switch millions of times per second. Vacuum tubes got super hot, wasted tons of energy, and would burn out all the time. Transistors, they're incredibly efficient and ultra-reliable. It was a total game changer. So, how in the world is this tiny marvel actually built? Let's move on and crack it open to see what's really inside the transistor. Every standard transistor has these three little legs, or terminals, and the names actually make a ton of sense. You've got the collector, which, you guessed it, collects the charge. The emitter emits that charge out into the circuit. And then there's the star of the show, the base. That's the control pin. That's our on-off switch that manages everything happening between the other two.
Structurally, a really simple way to think about a transistor is like two diodes just connected back to back. This is what creates its signature three-layer sandwich of semiconductor material.
And that little sandwich comes in two main flavors, NPN and PNP. An NPN transistor has a layer of P-type material sandwiched between two N-type layers. Now, this is by far the most common type, and it works just like our water valve. You give the base a high or positive signal to turn it on. A PNP transistor is just the reverse, a PNP sandwich, and you turn it on with a low signal. For the rest of this, we're just going to focus on the NPN type because it's the one you'll see everywhere.
Okay, now for the really, really cool part. Let's talk about flipping the switch. How do we actually turn this thing on? Well, it all comes down to this one magic number, 0.7 volts. For a standard silicon transistor, this is the critical threshold. It's the minimum voltage you have to apply to the base to turn the handle and open that valve for the current. Let's just see it in action. Here's a super simple circuit. We're applying a voltage to the base. So if that voltage is less than our magic number, let's say 0.5 volts, the transistor just sits there. It's non-conductive. It's basically an open switch, so no current can flow, and our little LED stays off. But the very moment we nudge that base voltage up to 0.7 volts or just a little bit more, the transistor flips. It instantly becomes conductive. It's like the switch is now closed. Current starts flowing through and, boom, the LED turns on. It's a perfect, simple, reliable electronic switch.
So what's the secret? I mean, what is it about this material that creates this magical 0.7 volt trigger? Well, welcome to Section 4, the semiconductor secret.
The key to all of this is a special class of materials called semiconductors, and silicon is the most famous one of them all. What makes them so special is that we can manipulate them. We can make them act as either a conductor, which lets electricity flow easily, or an insulator, which blocks it completely. That's the perfect property for building a switch, right? And how do we manipulate it? We use a process with a kind of cool name, doping. And no, not that kind of doping. In electronics, doping is the incredibly precise process of adding specific tiny impurities to pure silicon. And by doing this, we can carefully change its electrical properties, creating two brand new materials, N-type and P-type. First up, N-type material. This is what you get when you dope silicon with an element that has an extra electron to share. The result is you get a material with a surplus of free-moving electrons, just kind of hanging out. The easy way to remember it? N is for the negative charge of these extra electrons.
In P-type, you guessed it, is the total opposite. We dope the silicon with an element that's missing an electron. This creates a deficit, which results in these little empty spots we call holes. And you can think P for the positive nature of these holes, which really want to attract an electron. By layering these N and P materials together, we build that NPN sandwich that becomes our transistor.
Okay, let's zoom all the way back out. We've got our tiny switch, we know how it works, but why does this matter so much? This brings us to our last section, billions of digital brains.
I think this quote just says it all. Without transistors, we simply wouldn't have the luxury of computers and other digital devices. They are, without a doubt, the bedrock of the entire digital age.
So how do you get from one simple switch to a thinking machine? It all starts with binary. A single transistor state can represent a 1 when it's on, or a 0 when it's off. It's a physical bit. Now, if you group a few of these transistors together, you can create things called logic gates, which can make very simple decisions. Then, you just scale it up, way, way up. You string together billions of these logic gates all working together, and you get the incredibly complex brain of a modern computer processor. And when I say billions, I am not kidding. A single modern computer chip can have around 50 billion transistors packed inside it, each one a perfect little switch, flipping on and off millions of times a second. It's a scale that is just, honestly, it's mind-boggling.
So yeah, these tiny little switches, built from doped silicon, completely and totally rebuilt our world in less than a century. It kind of makes you wonder, right? What will the next tiny switch look like?